The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we've been developing the procedure to describe a quantum gas of identical particles. That are non-interacting. Okay, so what does that mean? It means that we are thinking about a Hamiltonian for a system of n particles. If they are not interacting, it can be written as the sum of the contributions for the individual particles. And if they are identical, it's basically the same particle for each one of them. Same Hamiltonian for each one of them. Okay, how do we handle these? Well, if we regard this as a quantum problem, for a single particle, so for each one of these Hamiltonians, we can find the eigenstates. So there's a bunch of states, let's say, labeled by k, because we ultimately have in mind the plane waves that describe gas particles in a box, and there's corresponding energy levels for the single particles, epsilon k. And the single particle spectrum therefore can be described by a bunch of energies, a ladder of energy levels with different values of k and different allowed discretized energies. Now, when we want to describe a case of n particles that are non-interacting, we said that we could, in principle, pick 1k here, 1k here, 1k here. And if we are dealing with bosons, potentially more than one at each site. And so the state will then be described by a bunch of occupation numbers, nk. And this nk will be 0 or 1 if we are talking about fermions, but any integer if we are talking about bosons. So this eta being plus or minus was used to distinguish appropriate symmetrization or anti-symmetrization. Now, once we have a state such as this, clearly the n-particle Hamiltonian acting on a state that is symmetrized with this bunch of occupation numbers will give us back the state. The energy that we would be getting is summing over all possible k values, epsilon k times the number of occurrence of that in this state, again multiplying the state back. Of course, we have a constraint that the number of particles matches the sum of the occupation numbers. Okay. So then we said, OK, this is just a description of the state that we want to describe, or the set of states that represent this system of identical non-interacting particles in quantum mechanics. So the next stage, we want to do some kind of statistics for them. And we had seen that basically, in order to assign appropriate statistics in case of quantum systems, we have to deal with the density matrix. And we saw that in the canonical representation, the density matrix is complicated and amounts to some kind of an interaction among particles. Although there is no interaction at this level, the symmetrization or anti-symmetrization creates states that are intermixed in a manner that appears as if you have an interaction. We found that, however, we could get rid of that by going to the grand canonical ensemble. Where we would trade in the constraint that the number of particles is fixed with the chemical potential. And in this ensemble, we found that the density matrix is diagonal in this representation. So the diagonal elements can be thought of as the probability of one of these occupation number sets. And so the probability of a particular set of occupations in this grand canonical prescription is proportional to e to the beta. Of course, we have mu if we are going to this grand canonical ensemble, minus epsilon k, and then we had nk. So the probability that a particular one of these is occupied nk times in this grand canonical prescription is simply an exponential. Now, of course, the different k levels are completely independent of each other, so the probability factorizes in this fashion. Of course, as any probability, we have to normalize this. Normalization is appropriately called the grand canonical partition function, and will be different whether we are dealing with Bose statistics or phonon statistics. And actually, because we have a structure such as this, Q is going to be the product of the normalization of each individual one. And therefore, log of Q is going to be a sum of the contributions that I would get for the normalization of each individual ones, and of course, the log of whatever normalization I have for the individual one. If I have the case of fermions, where nk gets 0 or 1 as the two possibilities, then the normalization will be simply 1 plus this exponential. And I choose to write that as z e to the minus beta epsilon of k, where I have introduced z to be e to the beta mu, because this combination occurs all the time. I don't want to keep repeating that. So this was for the case of fermions. For the case of bosons, where n goes 0, 1, 2, 3, etc., this is a geometric series. For the geometric series, when I sum it, I would get 1 over this factor. So when I take the log, I will have a minus sign here. And I can put the Bose and Fermi cases together by simply putting a factor of minus eta here, so that I have the plus for the case of fermions and the minus for the case of bosons. Okay? So this is one thing that we will be using. The other thing is that this is the probability for this level having a certain occupation number, nk. We can always ask what is the average of nk. And from this probability, it is easy to calculate the average. And the answer, again, can be collapsed into one expression for the case of bosons and fermions as 1 over z inverse e to the beta epsilon of k minus eta, encompassing both fermions and bosons. So these results give some idea both at the microscopic level in terms of occupation numbers of these different levels, and macroscopic level a grand partition function from which we can construct thermodynamics, actually a full probability again in this ensemble, which we can transform in principle and get density matrices, etc., in other bases. But these are the kinds of things that we can do for any interacting Hamiltonian. Okay. Now, what I said over here was that I'm actually interested in the case of a gas. So let's again think about the type of gas, such as the one in this room that we are interested. And again, to make a contrast with something that we may want to do later, let's emphasize that it is a non-relativistic gas. So the Hamiltonian H is essentially free particle in a box of volume V, the thing that we have been using all the time, just the kinetic energy of a one-particle state. And for that, we know that the single particle energy levels are characterized by a vector k, has 3 components, in fact, and h bar squared over 2m k squared. And we've discussed what the discretization of k is appropriate to the size of a box. We won't go over that. So again, maybe it is important to mention that because of the discretization of the k values, the spacing between possible values of k are 2 pi over L in each direction. And ultimately, what we want to do is to replace these sums over k's in the limit of large boxes with integrals over k. So these go over to an integral over k times the density factor that you get in going from the sum to the integral, which is 2 pi cubed times the volume. I will introduce one other factor here, which is that when we are talking about quantum particles and bosons and fermions, they are typically assigned also another state, another parameter that characterizes their spin. And depending on the possible values of spin, you will have g copies of the system. And this g will be related to the quantum spin through the formula 2s plus 1, so that when you have fermions, typically s is half integer, and this will be an even number, whereas for bosons, it will be an odd number. So that's, again, something that you've seen. It just essentially says multiply everything by some factor of g. Now, if I go through this procedure that I have outlined here, I will ultimately get the grand partition function of the gas, which, as we will see, is related to its pressure, in terms of the chemical potential. But throughout the course, we've seen that the more interesting thing to look at is how things depend on density rather than chemical potential. So I'd better use this result to get what the density is. How do I do that? Well, once I have determined what the chemical potential is, the average number of particles will be the sum over the average occupation numbers that I have in all of these states. And according to the prescription that we have over here, in the limit of a large box, this sum over k becomes g v integral d cubed k 2 pi cubed. Ultimately, I will divide by v, so I will have the formula for the density. And what is nk? Well, I have the formula for nk. It is 1 over z inverse e to the beta. Epsilon k is h bar squared k squared over 2m. And then I have a minus 8. OK? So if I divide through by v, clearly I will have the density. And get rid of this v. But I have to do that integral. Now, for this and a lot of other things, you can see that always I will have sums or integrations over the combination that appears in the exponent and hence is dimensionless, which is beta epsilon of k. So let me introduce a new variable. Let me call x to be the combination beta h bar squared k squared over 2m. So I'm going to call this e to the x, if you like. So I have changed variables from k to x. K in terms of x is simply square root of 2m inverse of beta, which is kt, divided by h bar squared. But I took a square root, so it's just h bar, times x to the 1/2. Okay? Now I realize that h bar is in fact h divided by 2 pi. So the 2 pi I can put in the numerator. And then I remember that actually the combination h divided by square root of 2 pi mkt, I was calling this thermal wavelength lambda. And k should have the dimensions of an inverse length scale, so that's the appropriate thing to choose. So what do I get? I take a square root of pi inside, and I'm left with 2 square root of pi divided by this parameter lambda, x to the 1/2. Again, for later clarity, let's make sure we remember this was our lambda. So this is the variable k that I need. In fact, for the integration, I have to also make a change in dk. So I note that dk, if I take a derivative here, I will get x 1/2 x to the minus 1/2 becomes root pi over lambda x to the minus 1/2 dx. Actually, the factor that I need over here is d cubed k over 2 pi cubed. Now, everything only depends on the magnitude of k, so I will take advantage of spherical symmetry, write d cubed k as 4 pi k squared dk divided by 8 pi cubed. And then I substitute from k squared and dk above in terms of this x. So I will have a 1 over 2 pi squared from this division. K squared is simply 4 pi over lambda squared x. This is k squared. dk is root pi over lambda x to the minus 1/2 dx. So you can see lots of things cancel out, and the answer is going to be x to the 1/2 dx divided by lambda cubed. And what is left from all of these pi's, etc., is a factor of square root of pi over 2, or 2 in the numerator, or square root of pi over 2 in the denominator. Okay? So if I do these set of changes that I have on the right part of the board, what do I have for density? The density becomes simply g. I have this integral over k that I have recast as an integral that is x to the 1/2 dx. Let me pull out the factor of lambda cubed on the outside. So I have g over lambda cubed. I will pull out the factor of root pi over 2 that I had before. And then I have the integral from 0 to infinity dx, x to the 1/2. Actually, let me write it in this fashion, dx, x to the 1/2. And in the denominator, what do I have? I have z inverse e to the x minus 8. So we did all of these, and we ended up with an integral that we don't recognize. So what we are going to do is to pretend that we recognize it and give it a name, right? So we define a set of functions f sub m of variable z. Once I do the integration over x, I will get a function of z. So that function of z I will call fm of z. But clearly, I have a different fm if I have eta of -1 or eta of +1 for bosons or fermions. So there is two classes of these. What's this m? OK. So here I had the integral x to the 1/2. It turns out that we will get a whole bunch of these integrals where the power that is out front in the numerator is different. So I will generalize this x to the 1/2, this 1/2 to something that I'll call m minus 1. And then I have z inverse e to the x minus eta. And it is normalized so that what is in front is 1 over m minus 1 factorial. Okay, so these are very important functions. Everything we will do later on, we will be expressing in terms of these functions. Now, clearly, what is happening here corresponds to m minus 1 being equal to 1/2 or m being 3/2. What is this normalization? Well, for the normalization, if this is 1/2, I would need 1/2 factorial. And if you go and look at the various definitions that we have for the gamma function or the factorial, you can check that 1/2 factorial is root pi over 2. And indeed, we saw this already when we wrote the expression for the surface area in general dimensions that involve the factorial function appearing as fractions. And in order to get the right result in 2 or 3 dimensions, you can check that this root pi over 2 for 1/2 factorial is correct. So indeed, I already have this root pi over 2 over here. It was properly normalized. So the whole thing here can be written as n is g over lambda cubed f 3/2 eta of z. That is the expression that relates the density to the chemical potential, or this combination e to the beta mu, which is z, or the fugacity, is simply this nice formula. Okay. So, but what we want is to calculate something like the pressure for the gas. Well, let me remind you that log Q, essentially quite generally, log Q comes from normalizing something that is like mu times the total number of particles minus the energy. You can kind of read that from here. And then there would be Ts from the number of states. This was the general formula that we had. And when we substitute for a system that is extensive, where E for a gas is mu n plus Ts minus Pv, we see that the log of the partition function is simply the combination beta Pv. Okay? Of course, again, this pressure as a function of density or chemical potential would be different whether we are thinking about bosons or fermions. But it can be calculated from the kind of sum that we have over here. So let's do that. So I have beta P, which is something like log Q divided by V, is obtained by doing this sum over K over V. And so what do I get? I will get, first of all, I have the minus eta. Sum over k I will replace with g. Integral over k divided by 2 pi cubed. The volume factor cancels because I divided by volume. I have log of 1 minus eta z e to the minus beta, again h bar squared k squared over 2m are the energy levels that I'm dealing with. Okay, fine. What do we do with this? We make the same change of variables that we have over here from k to x. So then I would have minus eta. d cubed k over 2 pi cubed gets replaced with this 2 over root pi lambda cubed. And then I have the integral 0 to infinity dx, x to the 1/2 log of 1 minus eta z e to the minus x. Huh. It seems like yes.
What happens to your factor, g?
G, good question. Anything else? So I was hoping to have integrals that are all expressible in terms of this set of functions that I defined. This log does not fall into that category. Should I define something else? Well, the answer is no, because I can make that integral look like this by simply doing an integration by parts. So we do integrate by parts. In which case, what I do is I take a derivative of this, and I take an integral of x to the 1/2. Integral of x to the 1/2 becomes x to the 3/2 over 3/2. There is, of course, a minus sign involved. So this minus becomes plus eta. Make sure I have the g this time. 2 over root pi lambda cubed. I have the integral from 0 to infinity dx. X to the 1/2 became x to the 3/2. The 3/2 I will bring out front, so I have 1 over 3/2 here. And then I have to take the derivative of this function. What's the derivative of the log? It is 1 over the argument of the log times the derivative of the argument of the log, which is minus eta z, the derivative of e to the minus x, which is e to the minus x, and this minus becomes plus. Okay, so let's arrange things a little bit. I can get rid of these etas, because eta squared will be 1. What is the answer, therefore? It is g over lambda cubed. That's fine. If root pi over 2 is 1/2 factorial, and I multiply 1/2 factorial with 3/2, what I will get is 1 over 3/2 factorial, because n factorial is n times n minus 1 factorial. And then what do I have? I have 0 to infinity dx, x to the 3/2. Divide numerator and denominator by z e to the minus x, and you get z inverse e to the x minus eta. And lo and behold, we have a function of the variety that we had defined on the other board, corresponding to m minus 1 being 3/2 or m being 5/2. So what we have here is that beta p, depending on whatever statistics we are dealing with, is g over lambda cubed f 5/2 eta of z. Yes?
Boundary terms in distribution.
Okay. So what you have to do is always ensure what is happening to the boundary terms. Boundary terms will be a product of x to the 3/2 and this factor. At x equals to 0, x to the 3/2 will ensure that you are 0. At x goes to infinity, the exponential will ensure that you are to 0. So the boundary terms are important, and indeed you have to check them, and you can check that they are 0. Okay?
I think the factor that multiplies x to the 3/2 is the log, not the, but it's, the argument still holds.
The argument still holds because as x goes to infinity, e to the minus x goes to 0, log of 1 is 0. In fact, you can ask, how does it go to 0? It goes to 0 exponentially. Exponentially will kill off any power law. Yes, thank you for the correction. Okay? All right, there's one other thing that we can take a look at. The total energy. Oh, okay. So the energy in each one of these states is given by that formula. So if I ask what is the total expectation value of energy, and again in thermodynamics we expect the extensive quantities such as the energy should have in a thermodynamic sense well-defined value, so I won't write the expectation value, is going to be a sum over k and k epsilon k. Again, this will depend on the statistics that I'm looking at. And what I will have is that this will go over to an integral over k divided by 2 pi cubed multiplied by g and multiplied by v. I have epsilon of k, which is h bar squared k squared over 2m. The expectation value of n, which is z inverse e to the minus beta, z inverse e to the plus beta h bar squared k squared over 2m minus 8. Okay. So the simplest way to do this is to first of all divide by v. So I can define an energy density. Actually, since I'm going to change variables to this combination that is x, I notice that up to a factor of beta, the numerator is x. So let me actually calculate the combination beta e over v that only depends on this combination x. So what is it? It is g. The integral over k, I know how to replace it with something that involves x, is going to give me 2 over root pi lambda cubed integral 0 to infinity dx. From the change of variables, I have x to the 1/2, but I introduced one factor of x here because I have this energy factor in the numerator. So that changes this to x to the 3/2, and then again I have z inverse e to the x minus 8. Okay. So it is one of the integrals that we have defined. In fact, it is exactly what I have above for the pressure, except that I don't have the factor of 3/2 that appeared nicely to give the right normalization. So what I conclude is that this quantity is, in fact, g over lambda cubed times 3/2 of f 5/2 eta of z. Okay? But they are exactly the same functions for energy and pressure. So you can see that irrespective of what the chemical potential is doing, I can state that for the quantum system, E is always 3/2 PV. Of course, we had seen this expression classically. Now, what happens quantum mechanically is that the pressure starts to vary in some complicated way with density. But what we learn is that energy will also vary in the same complicated way with density, such that always this formula E being 3/2 PV is valid. There is some nice symmetry reason for why that is the case that you will explore in one of the problems that you will see. Okay? So these are the characteristics. In some sense, we have solved the problem because we know both density and pressure in terms of chemical potential. So all we need to do is to invert this, get the chemical potential as a function of density, insert it in the formula for pressure, and we have pressure as a function of density. But since these are kind of implicit through these f functions, we don't quite know what that means. So the next stage is to really study how these f functions behave and how we can relate their behaviors to dependence on density. And we will see that we have to distinguish between low density and high density regimes. What does it mean? Well, you can see that what appears on the right-hand side is dimensionless. The only dimension full combination that we have here is n. Well, we can make it dimensionless by multiplying by lambda cubed over g. So it turns out that whether or not you see things that are classical or things that are very quantum mechanical depend on this degeneracy factor, which within our context of statistical physics of gases, we define to be the combination n lambda cubed over g. And we will regain classical behaviors when degeneracy is small, density is small enough such that d is much less than 1. And we will see totally new behavior that is appropriate to quantum mechanics in the other limit where d becomes large. Okay? So this distinguishes classical versus quantum behavior. Now, we expect to regain classical behavior in the limit of very low densities. That's what we've been kind of saying from the very first lecture, that low density gas has this ideal behavior where PV is nkt. And therefore, let's focus on the limit where d is much less than 1, which is classical. And since d is f 3/2 eta of z, we need the behavior of the function when it is small. And I'll show you self-consistently that the function is small when its argument is small. So we'll see that d less than 1 implies or is implied by z being less than 1. Okay? So let's take a look at one of these functions, fm eta z, 1 over m minus 1 factorial, 0 to infinity dx, x to the m minus 1, z inverse e to the x minus 1. And I'd like to explore the limit of this when z is small. So that's currently not very good because I have z inverse. So what I will do is I will multiply by z e to the minus x, both numerator and denominator. So I will have m minus 1 factorial, integral 0 to infinity dx, x to the m minus 1. I have z e to the minus x. I have, oops, there was an eta here. 1 minus eta z e to the minus x. Okay? Then I say, well, the thing that is appearing in the denominator, I can write as a sum of a geometric series in powers of z. And that's, after all, what I'm attempting to do, make an expansion in powers of z. It starts with z e to the minus x. And 1 over 1 minus eta z e to the minus x, I can write as the sum alpha going from 0 to infinity of eta z e to the minus x raised to the power of alpha. This geometric series sums to what I have over there. Okay? Let's rearrange this a little bit. I will take the sum over alpha outside. Well, I noticed that actually I have here this first term, which is different from this by a factor of eta. So let me multiply by an eta and yet another eta. And then I have a sum that starts from 1 to infinity of eta z e to the minus x to the power of alpha. So I have eta z to the power of alpha. I have one other eta here. And then I have the integration over x. X to the m minus 1. I didn't write e to the minus x to the alpha because I pulled it out of the integration. I will write it now, e to the minus alpha x. And I didn't write the 1 over m minus 1 factorial. Okay? Now, once more, this is an integration that you have seen. The result of doing integral dx x to the m minus 1 e to the minus x is simply m minus 1 factorial. Except that it is not e to the minus x, but it's e to the minus alpha x. I can rescale everything by alpha, and I will pull out a factor of alpha to the m. Okay? So what do we have? We have that fm eta of z has a power series representation, alpha running from 1 to infinity, z to the alpha divided by alpha to the m. It's an alternating series that starts with plus and then becomes minus, etc. So if I were to explicitly write this, you will see how nice it is. It is z plus eta z squared 2 to the m plus z cubed 3 to the m plus eta z to the fourth 4 to the m. And you can see why it is such a nice thing that really deserves to have a function named after it. So we call that nice series to be f. Okay. Now, for future reference, note the following. if I take a derivative of this function with respect to z, its argument, then in this power series, say z to the fourth becomes 4z cubed. 4 will cancel one of the 4s that I have here, and it becomes 4 to the m minus 1. This becomes 3 to the m minus 1. So you can see that the coefficients that were powers of m become powers of m minus 1. Numerator has gone down by 1 factor, so let's multiply by z. So the numerator is now what it was before. The denominators, rather than being raised to the power of m, are raised to the power of m minus 1. So clearly, this is the same thing as fm minus 1 of z. So basically, these functions have this nice character that they are like a ladder. You take a derivative of 1, and you get the one that is indexed by 1 less. Okay. In the derivatives?
I mean, it seems to me like there's an eta like in that relation that you...
In this relation?
Yeah.
Okay, so let's do it by step. If I take a derivative d by dz, I get 1 plus eta z squared z 2 to the m minus 1 plus z squared 3 to the m minus 1. Then I multiply by z. This becomes z. This becomes z squared. This becomes z cubed. And you can see that the etas are exactly where they should be.
Could you explain why the index of summation starts from
1.
1?
Okay. So let's take a look at this function. You can see there is a z inverse in the denominator. So I made it into a z here. So you can see that if z is very small, it will start with z. Right? Now what happened here? I wrote this as a sum of geometric series. I pulled out this factor of z that was in the numerator. And the denominator I wrote as a series that starts with 0. But then there is this z out front. I pulled this z e to the minus x in front here, and then it starts with 1. I could have written it, I can put this in here and write it as alpha plus 1 with alpha starting from 0, etc., or I can write it as alpha. Or alternatively, you can say, let's put the eta here and the eta here, and then I see that this is the geometric series where the first term is this z e to the minus x. Okay? So I want to erase this board but keep this formula. So let me erase it and then rewrite it. Okay? So this I will rewrite as n lambda cubed over g, which is my degeneracy factor, is f 3/2 eta of z. And in the limit where z goes to small, I can use the expansion that I just derived, which is z plus eta z squared 2 to the, 3/2 plus z cubed 3 to the 3/2 and so forth. Now you can see that precisely because as z goes to 0, this series goes to 0, that smallness of d is the same thing or implied by the smallness of z. But that z is equal to d only at the lowest order. So what happens at higher orders, z, inverting this, is d minus eta z squared 2 to the 3 halves plus z cubed 3 to the 3 halves, and so forth. And we saw this when I was doing the calculation for the interacting gas, that clearly to lowest order z equals to d. If I want to get the next order, I substitute the result of the previous order into this expression. So z I substitute for it d. I will get d minus eta d squared 2 to the 3 halves as the first contribution, and then something that is order of d cubed. And if I want the answer to the d cubed order, I take this whole thing that is at order of d squared and substitute it in this series. And so what do I get? I will get d minus eta 2 to the 3 halves square of z, which is the square of this quantity. Square of this quantity is d squared minus twice the product of these two terms. So I have twice eta d cubed 2 to the 3 halves, and then square of this term, but that's order of d to the 4th. I don't care for that. And then I have from here plus d cubed 3 to the 3 halves, ignoring terms that are order of d to the 4th. Okay? So z is
plus here. Z equals d minus and d plus.
great, thank you. Minus. Good. Saves me having to go back later when the answer doesn't match. Okay. Fine. Now let's organize terms. To lowest order, I have d. At order of d squared, I have still just this one term, minus eta d squared over 2 to the 3 halves. We knew that was the correct result at order of d squared. At order of d cubed, I have two terms. One is the product of these two terms. The etas disappear, minus 2, and this will give me 2 over 8, which is 1/4. And from the other part, I have 1 over 3 to the 3 halves d cubed, and I haven't calculated things at order of d to the 4th. Okay? Fine. So we have calculated in a power series that we can go to whatever order we like, this z, which is related to chemical potential, as a function of this degeneracy that is simply related to density. Now, the formula for the pressure is up there. It is that beta p is g over lambda cubed f5 halves eta of z, right? So reorganizing this a little bit, the dimensionless form is beta p lambda cubed over g, f5 halves eta of z. f5 halves, we can make an expansion. It is z plus eta z squared 2 to the 5 halves plus z cubed 3 to the 5 halves, and so forth. For z, I substitute from the line above. So I have d minus eta d squared 2 to the 3 halves plus 1/4 minus 1 over 3 to the 3 halves d cubed. So that's the first term. The next term is eta 2 to the 5 halves z squared. So I have to square what is appearing here, keeping terms to order of d cubed. So what do I have? I have d squared from squaring this term, and a term that is twice the product of these two terms. That's the only term that is order of d cubed. So I have minus 2 eta 2 to the 3 halves d cubed. And finally, z cubed over 3 to the 5 halves will be d cubed over 3 to the 5 halves. And I haven't calculated anything at order of d to the 4th. OK? So what do I have? I have that beta p lambda cubed over g. Well, you can see that everything is going to be proportional to d squared d cubed. So let's pull out a factor of d, which is n lambda cubed over g. So this is just one factor of d that I have pulled out. So that then I start with 1. And then the next correction, I have an eta d squared 2 to the 3 halves here, eta d squared 2 to the 5 halves here with opposite sign. So this is twice bigger than that. So the sum total of them would be minus eta divided by 2 to the 5 halves times d squared, one factor of d I have out front. The other factor I will write here, n lambda cubed over g. And then at order of d cubed, I have a bunch of terms. I have a 1/4 here. And from the product of these terms, I will have etas disappear. I have 2 divided by 2 to the 8 halves, which is 2 to the 4th, which is 16th. So the product of these things will give me a minus 1/8. I have 1/4 minus 1/8. I will get 1/8. And
oh no, we have 8 squared. Yeah.
OK. And then we have minus 1 over 3 to the 1 half, and this 3 to the 5 halves. This is 3 times larger than this. This is 3 over 3 to the 5 halves. Subtract one of them, I will be left minus 2 divided by 3 to the 5 halves n lambda cubed over g squared, and so forth. So you can see that the form that we have is beta p, the pressure, starts with density. I essentially divide it through by lambda cubed over g. I start with the ideal gas result, n. And then I have a correction that is order of n squared. I can write it as v2 n squared in view of our virial coefficients. And we see that our b2 is minus eta times, minus eta 2 to the 5 halves times n lambda cubed over g. Remember that B2s, etc., had dimensions of volume. So the volume is provided by lambda cubed. It is an additional factor. It's for fermions, it's a positive pressure. So the pressure goes up because fermions repel each other. For bosons, it is negative. Bosons attract each other. And we had actually calculated this. We did a calculation of the canonical form where we had the one exchange corrections. And if you go back through the notes, or if you remember, we had calculated precisely this. But then I said that if I went and tried to calculate the next correction using the canonical formulation, I would have to keep track of diagrams that involve 3 exchanges and all kinds of things. And it was complicated. But in this way of looking at things, you can see that we can very easily compute the third virial coefficients and higher orders. In particular, the third virial coefficient we compute to be 1/8 minus 2, 3 to the 5 halves lambda cubed over g squared. And you can keep going and calculate higher and higher order corrections. Yes?
If you're doing this expansion for z being close to 0,
Yes.
that means that chemical potential is a large negative number.
Yes.
What kind of interaction does it imply between our grand canonical ensemble and the system from which it takes particles? Because chemical potential represents, like energy threshold for the particle to move from 0 to.
Okay. So as you say, it corresponds to being large and negative, which means that essentially, I think the more kind of physical way of looking at it is this: z is e to the beta mu is the likelihood of grabbing and adding one particle to your system. And what we have is that this is much, much less than 1. And the way to achieve that is to say that it is very hard to extract and bring another particle from whatever reservoir you have. And it is because it is so hard that you have such low density of particles in the system that you have. So for example, if you are in vacuum and you put a surface and some atoms from the surface detach and form a gas in your container, the energetics of binding those atoms to the substrate particles was huge, and few of them managed to escape. Okay? All right, but this is only one limit, and this is the limit that we already knew. We are really interested in the other limit, where we are quantum dominated. And clearly, we want to go to the limit where the argument here is not small. I have to include a large number of terms in this series. And then I have to figure out what happens. I mean, how do I have to treat the cases where I want to solve this equation, and the left-hand side, d, is a large number. So how can I make the value of the function large? What does that imply about the argument of the function? Okay? So different functions will become large for different values of the argument. And as we will show, for the case of bosons, these functions become large where the argument becomes 1, whereas for fermions, they become large when the argument itself becomes very large. So the behavior of these functions is very different. When they become large at different points when we are thinking about bosons and fermions. And because of that, at this stage, I have to separately address the two problems. So up to here at the high temperature limit, we sort of started from the same point and branched off slightly by going in the boson and fermion direction. But when I go to the other limit, I have to discuss the two cases separately. So let's start with the case of fermions. So degenerate in the sense of d being larger than 1 rather than character flaws. So what do we do in this limit? So what I need to know is to look at one of these functions. So let's say we have d n lambda cubed over g is f3/2 minus of z, which is 1 over this 1/2 factorial, integral 0 to infinity dx x to the 1/2. And here I have a plus because I'm looking at the fermionic version of these. I have z inverse e to the x, and I can write that as e to the x minus log z. Okay? Now, essentially, if I look at this function, actually, let's look at the function that is just 1 over e to the x minus log z plus 1 as a function of x. What does it do? In the limit where z is large. In the limit where z is large, log z is also very large. And then what I have is something that if x is much less than log z, essentially this factor will be 0, and I have 1. Whereas if x is much greater than log z, then this is exponentially large quantity, and I will have 0. So basically, at around log z, this switches from being very close to 0 to being 1. Indeed, at x equals to log z, it is exactly 1/2. So here it is 1/2. It is switching very rapidly. And you can see that essentially the value of the function depends on the combination x minus log z. So if I were to make log z much larger, I'm essentially transporting this combination without changing its shape, either in one direction or in the other direction. Okay? And if I go to the limit, essentially that log z is very large, I will have 1 for a huge distance, and then at some point I would switch to 0. And what I'm doing, therefore, is to essentially approximately integrating from 0 to log z x to the 1/2 dx, which would give me x to the 3/2, sorry, log z to the 3/2 over 3/2. And you can see that I can repeat this for any other value of m here. I would be integrating x to the m minus 1. So you would conclude that the limit as z is much, much larger than 1 of one of these functions fm minus of z is obtained by integrating 0 to log z dx x to the m. I will get another factor of log z, and then I will get log z to the power of m divided by 1 over m multiplying by 1 over m minus 1 factorial. It will give me m factorial. Okay? Now, of course, there will be correction to this, because this function would be equal to this if I was integrating a step function. And I don't have a step function. I have something that gradually vanishes, although the interval over which it vanishes is scaling much smaller than log z. So what you can do is you can do some manipulations and calculate corrections to this formula that become significant as log z is not exactly infinite, but becomes smaller and smaller. It turns out that that will generate for you a series that is inverse powers of log z, and in fact, inverse even powers of log z, so that the next term will fall off as 1 over log z squared. The next term will fall off as 1 over log z to the 4th, and so forth. And the coefficient of the first one, and I show you this in the notes, how to calculate it, is pi squared over 6 times m minus 1. The coefficient of the next term is 7 pi to the 4th 360, m minus 1, m minus 2, m minus 3. And there's a formula for subsequent terms in the series, how they are generated. And this thing is known as the Sommerfeld expansion. Okay. So essentially, if you plot as a function of z one of these fm minuses of z's, what we have according to the previous expansion, as you go to z equals to 0, you have a linear function z, and then the next correction is minus z squared. You start to bend in this direction, and then you have higher order corrections. But we see that at large values it keeps growing, and the growth at large values is this. So here you have z minus z squared 2 to the power of m. Out here you have log z to the m over m factorial, and then these corrections from the Sommerfeld expansion. Okay? And so once we have that function, which is the right-hand side of this equality, for a particular density, we are asking what is the value of z. And at low densities, we are evaluating solutions here. At high values of density, we are picking up solutions from this other limit. Okay? So let's imagine that we are indeed in that limit. So what do we have? We have that n lambda cubed over g is log z to the 3/2 over 3/2 factorial. That's the leading term. Sub-leading term is 1 plus pi squared over 6. M in our case is 3/2. M minus 1 would be 1/2 divided by log z squared. I will stop at this order. That's all we will need. And so I will use this to calculate z as a function of n. Again, same procedure as before. I can invert this and write this as log z being 3/2 factorial n lambda cubed over g. So I multiplied by this. I have to raise to the 2/3 power, the inverse of 3/2. I take this combination to the other side. So I have 1. This becomes plus pi squared over 8, 1 over log z squared, raised to the minus 2/3 power because I had to take it to the other side. Okay. So at the lowest order, what I need to do is to calculate log z from the 0th order term, and then at the next order, substitute that value of log z in here and get the next correction. So the lowest order correction will tell me that log z, which remind you is simply beta mu, is this combination raised to the 2/3 power. What is that combination? 3/2 factorial. 3/2 factorial we saw was 3/2 1/2 factorial, which was root pi over 2. So this is 3/2 factorial. I have n over g. Oh, sorry, n lambda cubed. So write it in this fashion. N over g And then I have lambda cubed. Let me put this to the 2/3 power, because lambda cubed to the 2/3 power is simply lambda squared. And lambda squared is going to be h squared divided by 2 pi m kt. So this is lambda cubed. What I'm going to do is notice that one of these h over 2 pi's is in fact already an h bar. I'd like to write the result in terms of h bar squared divided by 2m. The 1 over kt I can write as beta. Ultimately, it is my intention to cancel that beta, which is the 1 over kt, with the beta that I have out here, and get a value for mu. Okay. To go from h squared over 2 pi to h bar squared over 2m, I need a factor of 4 pi squared. Those 4 pi squared I will put out front in here, and they will change the result to something that is like this. It is n over g is going to be remaining there. I have pi, by the time it gets in front, over here becomes pi to the 3/2. Pi to the 3/2 multiplied by pi to the 1/2 becomes pi squared. You can convince yourself that the factors of 2 and all of those things manage to give you something that is 6 pi squared n over g to the 2/3 power. Yes?
So it would seem that the chemical potential has no temperature dependence.
Exactly. When you go to 0 temperature, the chemical potential of a Fermi gas goes to a constant that you have actually seen, and I just was about to make it clear to you what that constant is. So we get that limit as essentially this t goes to 0, which is another way of achieving the combination n lambda cubed over g goes to infinity. When t goes to 0, lambda goes to infinity, this combination becomes large. Canceling the betas, the limit of mu is something that potentially in solid state courses you have seen as the Fermi energy. And the Fermi energy is h bar squared over 2m, some Fermi momentum squared. And hopefully the Fermi momentum is going to come out to be 6 pi squared n over g to the 1/3. And one way that you usually get your Fermi momentum is you say that what I need to do is to fill up all of the states up to some value of kf. And the number of states that there are is the volume of the sphere, 4 pi over 3 kf cubed, of course, times the volume times the degeneracy coming from spins if I have multiple possibilities. And this should give me the total number n. So I made some big mistake here. Can somebody point it out to me? How do you calculate Fermi momentum and Fermi energy? It's not coming out the answer that I want.
1/8 of the sphere, right?
No, it's a sphere.
Divide by 2 pi.
Thank you. Divide by density of state. I multiplied by the v, but I forgot the 2 pi cubed here. Okay. So when you divide 4 pi divided by 8 pi cubed, you will have 2 pi squared times 3, which will give you 6 pi squared. N over v is the density divided by g. So you can see that we get the right result. Yes.
Q.
F cubed. Yes, that's right. So Kf is 1/3 of that. Let's go step by step. Is 6 pi squared n over g to the 1/3. Kf squared would be the 2/3 power, which is what you have. Yes.
So you said that this is the lowest order term for the chemical potential.
Exactly. Yes.
But aren't there going to be maybe a second order temperature dependent term?
Yes. So when we substitute that formula in here, we will find the value of the chemical potential. So I will draw it for you, and then we calculate the result later. So this is the chemical potential of the Fermi system as a function of its temperature. What did we establish so far? We established that at 0 temperature, it is in fact epsilon F. We had established that at high temperature, this was the discussion we had before, it's large and negative. It is down here. So indeed, the behavior of the chemical potential of the Fermi gas as a function of temperature is something like this. And so the chemical potential at 0 temperature is epsilon F. As you go to finite temperature, it will get reduced by a factor that I will just calculate for you. Okay? So if I now substitute this result in here to get the next correction, what do I have? Okay, so this 0th order term we established is the same thing as beta epsilon F. And then the next order term will be 1 plus this log z is going to be small, minus 2/3 times this is going to give me minus pi squared over 6. Right? And then I have 1 over log z squared. 1 over log z is simply 1 over beta epsilon F, which is the same thing as kT over epsilon F squared. So what we see is that the chemical potential starts to be epsilon F, and then it starts to go down parabolically in temperature. And the first correction is of the order of kT over epsilon F. Not surprisingly, it will go to 0 at a value t that is of the order of epsilon F over kB. So the chemical potential of the Fermi gas actually changes sign. It's negative and large at high temperature. It goes to the Fermi energy, which is positive at low temperatures. So once we know this behavior of the chemical potential, we can calculate what the energy and pressure are. And again, at 0 temperature, you will have some energy which comes from filling out this Fermi sea. And then we will get corrections to energy and pressure that we can calculate using the types of formulas that we have that relate pressure and energy to F5/2 of z. And so we can start to calculate the corrections that you have to a completely filled Fermi sphere, and how those corrections give you, say, the linear heat capacity is something that we will derive next time.